Catch me if you can. 2, 1, 4 over 3, 1 over 2, 8 over 15, 1 over 6. Then, what comes next? Give it a try. Does anything come to mind? At first glance, there's no obvious pattern, so I'll give you a hint. These numbers are rational coefficients from formulas that always involve pi and radius r, which means circles and spheres. This sequence comes from the volume formulas of spheres in different dimensions. A one-dimensional sphere is simply all points within distance r from the center, a line segment of length 2r. That length is its volume, so the coefficient is 2. A two-dimensional sphere is a circle. Its volume, its area is pi r squared, so the rational coefficient is 1. This is the volume of a three-dimensional sphere. The coefficient is 4 over 3. If we continue, one over 2, 8 over 15, 1 over 6. So, what is the rational coefficient for a 7-dimensional sphere? Do you know what the formula is? To answer this properly, we need the general formula for the volume of an n-dimensional sphere. Let's derive it. To do that, we introduce a carefully created integral. Let's call it I. I is defined as the integral of this exponential function over the entire n-dimensional space. This is called Gaussian function. So, we integrate this Gaussian function over all possible values of x1 through xn. We'll compute the same integral in two different ways. First, using Cartesian coordinates. Then, using spherical coordinates. Both calculations must give the same result. That equality is exactly what we need. In Cartesian coordinates, the exponential splits completely. The exponential becomes a product of n identical one-dimensional terms. So, the entire integral factorizes into n identical Gaussian integrals. Each one evaluates to square root of pi. So, the result is pi to the power of n over 2. Now, let's compute the same integral using spherical coordinates. Look at the exponent. It depends only on the distance from the origin. That distance corresponds to the radius of the n-dimensional sphere. As a result, all points at the same radius have exactly the same function value. So, instead of integrating point by point, we group points by radius. Since the distance from the origin is r, the function becomes e to the power of minus r squared. We then multiply this value by the surface area of the sphere at radius r. The integral I is therefore equivalent to integrating these contributions from r equals 0 to infinity. So, the only remaining piece is the surface area of the sphere. Here's a crucial geometric fact. As the surface of a three-dimensional sphere is a two-dimensional surface, in n dimensions, the surface of a sphere is an object of dimension n-1. And geometric quantities scale with radius according to their dimension. Lengths of 1D scale like r. Areas of 2D scale like r squared. Volumes of 3D scale like r cubed. So, an object of dimension n-1 must scale like r to the power of n-1. That's why the surface area of an n-dimensional sphere is proportional to r to the power of n-1. We write the surface area as k times r to the power of n-1. K is the surface area constant. Substitute the surface area formula back in this expression. The integral I becomes this. Now, we integrate over r. After a simple change of variables, the remaining integral matches exactly the definition of the gamma function, which is the extended function of factorials. Therefore, the integral I becomes this. But earlier, we already computed I. It was pi to the power of n over 2. So these two expressions must be equal. Setting them equal allows us to solve for k, the surface area constant of the n-dimensional sphere. Since the surface area is defined as k times r to the power of n-1, this is the surface area formula of an n-dimensional sphere. The volume of a sphere is obtained by integrating each surface area with respect to the radius. Carrying out that integral leads to a remarkably clean result. The volume of an n-dimensional sphere of radius r is equal to this. This is the general formula for the volume of n-dimensional spheres. Eventually, we are ready. Set n equal to 7. After simplifying the gamma function, the volume becomes this. So, the rational coefficient is 16 over 105. That's the answer. Today, we derived the volume formula of spheres in n dimensions purely through logic and mathematics. Unexpectedly, this formula turns out to be deeply connected to artificial intelligence and modern machine learning. That story is coming next. So, like and subscribe for the next. Thank you.